Okay, thank you so much for joining our presentations today. Today we will be presenting hiding objects from computer vision by exploiting the correlation biases. And in our group, we have three researchers, me, Imin Papar, and Paul, and Masaki Kamizuno. But today we are presenting, me and Paul will be presenting today. So before it, let me introduce myself. I am Jimin Papar. I am originally from Myanmar and currently working as a senior researcher and manager at Deadlight Japan. And my research interests include network security, malware analysis, IT security, web security, and AI security. I did several international research collaboration with universities in Myanmar, US, and in Netherlands and Germany. And you can find more about me on my website. And let me pass to Paul.
Okay.
Paul, could you please introduce yourself?
Of course. So, hi, my name is Paul Ziegler. I'm the founder and CEO of a company called Reflare, and I'm originally from Germany, but I've been living in Japan for the last 16 years and working here as well. I'm a consultant and advisor on information security issues to large companies and other consultancies, mostly with a focus on research and development. I'm completely self-taught, and that has given me a relatively shallow, but in turn very wide understanding of computer security, which in turn really helps me and my customers do research. Back to you, Papa-san.
So let me introduce our another member, Masaki Kamizuno. He is the CTO and partner of Deadlight Japan, and he engages in server research and new service development. And he also manages a lot of large-scale projects and design socially supportive demonstrational experiments that utilize these research results. And he contributes a lot to human resource development through the publications of papers and lectures. So before we get into the details of the studies, let me give you the executive summaries of our results. So in this study, we found out that the computer vision systems have an implicit correlation bias that must be accounted for. So if you take a look at the figure on the right side, you will see that the stop sign in the figure is totally hidden by major cloud vision system. And this happens because of the correlation bias we call. The stop sign and the food rarely exist together in nature. So with this correlation bias feature existing in nature, we can easily hide the stop sign in the figure. So it's easy. It's possible to completely hide the stop sign by contextualizing it with other non-correlating object, like here in this figure, the food. So if the detection rate of the objects through the computer vision system is critical, we need to train on specialized data sets that equalize the training bias. And this can mitigate the risk of this kind of attack. So let me give some important notes. So throughout these presentations, unless we stated otherwise, all evaluations are performed against University Street trained on COCO 2017 datasets. And here in our presentation, major cloud vision AIs refer to computer vision APIs provided by Google and Microsoft. And in order not to single out which one is better or good, we will only represent this category as a total detection percentage. All evaluation against the cloud vision AIs were performed on March 8, 2021. So it's likely that the features updates to these systems will lead to changes in the detection behavior. So let me give you a very much simplified recap of the computer vision technology. So image classification is like there is a stop sign in this picture, and object detection say there is a stop sign at this location in this picture. And the object segmentation say this is the outline of the stop sign in the picture, and the certainty say I am X% certain It just saying the certainty, X% certain that there is a stop sign in this picture, for example, like 80% sure this is a stop sign. And the threshold means I will detect the stop sign in this picture if my certainty is over X%, or for example, like a 50% or 60%. So let me give you how we find out the correlation bias features at the beginning of our study. So in the beginning of our study, we automatically generate thousands of composite images. We just combine each other. From the public data set, we take out a lot of graphics, and then we do a lot of composite images, and then we find out that the certain classes of identification errors exist. And so let me give you some examples of these identification errors we find out. So the first one is like we found out that the misclassification happens in the same general category. For example, if you take a look at the figure, you will see that the dogs and cats are seen as the combination of dog face and cats are seen as horses. And it's caused by mixing of features used to identify each class. So in most computer vision systems, detection is done through feature clusters extracted through the convolutional layers. That's why combining features from different classes can easily make this happen in the same general category. So this is the one identification error we found out in the beginning of our study, and the second identification error we found out is like a misclassification happened as part of something else. For example, like if you take a look at the figure here. The plant of course the flower on a shot worn by the person is seen as it's totally hidden, and it's only seen as a person. So this is caused by unclear logical line between objects. So like a person standing in front of a house should clearly be detected as a person, but in this case, why not a plant on a shed? It should be detected as well, but in this case it's totally hidden. So it's in the same way like a floral pattern on the round table. It's the same way because of the unclear logical line between the objects. So we found out this kind of identification errors exist. And the third identification error we found out is that the misclassification by correlation. For example, if you take a look at the figures, you will see that the round object next to the dogs is seen as a frisbee because it is caused by the high correlation between the two classes in the training data set. In this case, in the training data set, the dog and the frisbees appear mostly together in the training data set. That's why the computer vision system think of it as any round shape near the dog will be the frisbee. So in this case also, this round shape near the dog face is seen as a frisbee. So these features, we mainly use this feature exist in nature. I need to point out this because this kind of bias exists in nature and not just in the data set. So dogs and frisbees are often seen together in nature. So this main feature we use, we call this a correlation bias, and we use these features to generate a lot of several adversarial images. And you can take a look at some of the dog and frisbees figure in the COCO data set. So we have a lot of dog and frisbee always together. So we abuse this correlation existing almost always together, like dog and these frisbees. This kind of correlation bias to have to generate a lot of adversarial images. So Paul, could you please?
So let me take over from here. Now that we found this correlation of objects and how they are absorbed by machine vision systems, by computer vision systems together, we can establish that certain classes correlate, and we can establish that certain classes do not correlate. And based on that, we can automate the process of generating images that either have a very high correlation between objects or a very low correlation between objects. So switching from dogs to stop signs, because that's a much more interesting topic for machine vision, you can see here that we simply calculated, based on the COCO data set, what objects relate to stop signs. If you have the table on the left, you can see that cars and people have a very high correlation, traffic, lights, and trucks as well. And then it very much falls off drastically. Out of the 90 or so categories available in the 2017 COCO data set, only about 5%, only 11 have a 5% or higher correlation to stop signs in general. And what's important to note is that you can see that two classes have a correlation factor that exceeds 100%, namely cars and people exceed 100%. And the reason for that is that we counted each instance of an object while making these calculations. So let's say we have an image and it includes a stop sign, and it also includes 2 or 3 cars. Then each of these cars is counted individually, because, well, if one object is usually shown with clusters of other objects, then that is important as well. And that is why, on average, in every picture that has a stop sign in it, you have 1.6 cars. Thus, the correlation is 160%. So, how do we generate our images? First, we take a random picture of the target class. In this case, it's a stop sign, and we make sure it's detected. So we run a machine vision, computer vision system, and we see what the detection rate is. In this case, the stop sign is detected with a 98% accuracy. We do this step because we want to avoid using images where the detection rate is bad at the beginning, because there's no use in testing any of that. So we have an image, and it's seen by the AI. And then we cut that out. We use the segmentation mapping in the data set, and we cut out the object and we post it onto a background full of low correlation items. So in this case, it's a kitchen. It's a kitchen with a bunch of bottles and jars, and those are all items that do not correlate to stop signs. And we measure the detection certainty. Again, in this case, you can see it's down to 72%. And then, well, we get into this loop. It just goes on and on like this. We take a picture from the public data set, we select something, in this case a stop sign, any image with a stop sign in it at random, and then we test if it's well detected. In our final evaluations, we used ResNet 50, YOLO version 3, and Tiny YOLO, and only if all of them had a detection rate exceeding 95%, a certainty exceeding 95%, we proceeded. Cut it out, and then we select another image with a correlation of under 5% and paste them together, creating a new composite, and then we run the detection again. And only if all 3 networks now have a certainty of under 5% do we proceed and do we save the image as an adversarial image. I'll give you a short demonstration of the tool in action soon, but you can always access the source code from this URL. We've put it on GitHub, and it's MIT licensed, so feel free to do your own testing. Just be aware, as Papa-san stated in the beginning, that all of our tests against commercially available AIs were done in March, and updates are almost certain to improve detection rates over time. So here's a quick video demonstration of what's happening. It's just a Python script. It's a Python loop. You can see that I've passed the category class 13, which has correctly been identified as belonging to stop signs. We're loading in the training data from JSON. There's a bunch of output from CUDA and TensorFlow as they initialize. Give it a second. And once that's done, it builds all the networks. It initializes all the networks for the 3 computer vision algorithms that they're using. And then it runs the loop that I've just described to you. It goes in, it takes a picture, it identifies the initial minimum certainty, it generates a composite, it runs detection again, it checks for the minimum detection, and so on and so on. It's simply running as a loop. And again, you can run this at any time. We ran most of our tests on a 2080 Ti from NVIDIA. It should work flawlessly on any card with a comparable spec sheet. So what are some examples? Well, first, let me show you some examples that are created by only using YOLO 3 as both a first step and last step identifier. So YOLO 3 is used to determine if the stop sign is detected in the original image. And it's also used to determine if it's not detectable in the second image. With one single network, you can get some very impressive results. For example, this stop sign here is hidden. This is a case of overlap. The car and the stop sign have no real logical boundary. The stop sign is too large in relation to the car, so the machine vision system simply treats it as part of the car. The stop sign itself disappears. As a second example, the stop sign is also hidden. And this is a very common correlation that we found, or rather lack of correlation. Fruit, all sorts of food, pizza, dishes, they have virtually no correlation to stop signs because, well, when do you ever see them together? And so if you put a stop sign over a background of fruit or over a background of similar items, it is very likely to disappear. Plus, fruit has a very high entropy in its visual features. So there's lots of different fruits, a lot of different shapes. So it's very easy to hide an object like a stop sign among them. Similarly, sporting events, people playing sports, people themselves are very high correlation, but things like baseball gloves, baseball bats, chairs, they're not. So putting a stop sign over a scene of sports will also hide it. However, this is only for a single network. What we did then is we added more networks in. Instead of just using YOLO 3, we also added in ResNet, we added in TinyYOLO. And with all of them as classifiers, the images became a little less flamboyant, but they became much more reliable. So in this case, this is an example of an image that was generated against all three of them. And what happened before is all of these images that were only generated using YOLO 3 had about 50% chance of being detected by the other two networks. So yes, they were fooled by in about half the cases, but by increasing the number of networks, we hoped to push the quality of our adversarial images even higher. And well, ultimately, we want to generate something that's very universal. So as you can see, this dog with a stop sign, the stop sign is hidden, and it's again by correlation, by lack of correlation to the dog, and by a lack of correlation to the boat. Papa-san, back to you.
So we generate several adversarial images using the way that Paul explained, and so we generate images, and then we randomly choose the 1,000 adversarial sample images, and then we test these images against the major cloud vision AI, so that we know about the detection rates. So here is our result. So firstly, we choose the detection rate with certainty above 50% across these 1,000 random adversarial images. And here is the result of vendor A and B. So in case of Cloud Vision AI vendor A, out of the 1,000 adversarial images we tested, only 102 images above the 50% certainty is detected. And in the same way, vendor B, out of 1,000 images, 68 images are detected. So we can say like a detection percentage of 10.2% and 6.8% for each of the vendor. And here, the average certainty of the detection is for the vendor is 74%, and for the vendor B is 57%. And if you take a look at the figure on the left side, you will see that this figure is totally hidden in both vendor A and B. So while there were gaps in both the certainty and detection rate between the vendors, both systems were fooled by the majority of the adversarial images we generated. So here I will give you an impact of adding more networks while we generate the adversarial images, and we tested it against the vendor A. And so the figure is saying is that wherever we put more network while we generate the adversarial images, the detection rate is getting low. So this is the good result of this theory. And we also tested against the physical objects, and let me pass it to Paul.
Yes, of course. Having this in a digital realm is all nice and good, but it would be really interesting if we could, well, pull it off in the real world. After all we're doing is compositing. We don't have to obscure anything. We simply place a background behind an existing object and hiding it through that contextualization. So we now were at a point where we wondered, can we do that with real life objects? Can we do that with physical objects? In theory, we should be, but you never know until you try. So we made a small stop sign out of cardboard. We got a real stop sign as well, but turns out it was too big to pragmatically print backgrounds for it. So we got a small stop sign. We took a picture, and we used that picture as input. And as you can see on the left, it had a certainty exceeding 95% across all of the networks that we're using. And then on the right, we took a background that we knew worked in the digital realm to hide stop signs, and we put the physical stop sign on top of it, and it was undetected by 4 out of 5 networks, including one of the CloudVision systems. So this has some interesting implications for many things. Of course, self-driving cars are what immediately comes to mind. Naturally, those rely on LiDAR technology. They are naturally not only reliant on machine vision, but there's many implications here. You can reasonably expect objects to be hidden by simply contextualization through the background. So what can we do to prevent this? We had a couple of ideas of how to mitigate this problem, and luckily one of them worked really well. So here's what we did. We created a sample adversarial data set with 1,492 samples. And then we tested that data set against the standard YOLO version 3 COCO network with a detection rate of 0.00%, which of course it should be. We used that network to create the adversarial images, but it's always good to be sure. And then we took 200 images and added those to the training data, and we took 70 images and we added those to the valuation data of the COCO data set. And the remaining 1,222 samples remained as the test group. And then we did transfer learning. So we took an existing YOLO 3 network trained on COCO, and we trained it on the new data set for 2 hours. We kept that time short on purpose because we wanted it to be, well, a reasonable approach for mitigation. And then once the training was complete, we once again set the network to identifying objects in the remaining 1,222 test images to see how the detection rate would change. And these are the results. On the left, you can see the regular YOLO 3 network trained on COCO. And you can see that we had a 100% failure rate. And then after 2 hours of transfer training with 200 samples, we are now up to a 98%-ish detection rate. And we achieved this by simply adding 200 images, which is good because the COCO 2017 dataset has in excess of 118,000 samples. So we only had to have a mix-in of 0.16% to completely eliminate the problem. Now, we ran some other tests as well. We were worried that this might decrease the accuracy of the network in general. So we ran a standard test to determine the mean average precision, or MAP, of the new network. And the original map was 57.8. The retrained map was down to 57.7. However, the considered range that was normal at the time of testing for a map for a YOLO 3 COCO network was between 55 and 58. So while there is a minuscule decrease, it is very much in the realm of normalcy. However, it is important to note that we're only testing this against a single class. If you have a network that deals with hundreds or thousands of classes, it might have a bigger impact if you try to introduce adversarial images for each of the classes.
So in this session, I will give you some of the benefits of the correlation-based attack. So the very first point, our study is different from others. It's like ours is not the data set specifics or network specifics. So it means the adversarial generation process doesn't have to be repeated for each new target networks or data set, and it should work well across new version of the data sets. And the second point is it works on the physical objects too. So we deploying several adversarial images as backgrounds pasted behind the physical objects. I think Paul already showed the physical objects of the stop sign also allow for attacks against physical infrastructure. And the third benefit is that it can be deployed against unknown targets. So even the black box space. So since the correlation bias exists in the real world, they are relatively universal across several different data sets. This allows for attack against unknown computer vision system. And the other point is the target object doesn't have to be obscured or changed in a study. So in a case, we don't change anything. We don't anything on stop sign. We don't paste or put anything on the stop sign. And so in other approaches, it often requires at least a part of the target objects. For example, stop sign is need to be changed or covered by something else. So it works whether obscured or changed in our case. Okay. So that's all of our presentations, and all the questions and comments are welcome. Thank you.